Hello students, today we will start the space spectrum communication jamming as second type of the jamming and spectrum communication techniques, which is the frequency hopping space spectrum systems. Frequency hopping space spectrum system is another type of a space spectrum technique where the center frequency of the transmission of the carrier frequency will be periodically changing according to some PN sequences. How it is something like this? Suppose we have a wide band of channel available, which is equivalent to the signal bandwidth available for the transmission. Given this wide bandwidth of say W, we will divide this available bandwidth into several channels. Say I have capital N number of channels. Now, my carrier frequency of data transmission will be hopping from channel 1 to channel 2 to channel 3 to channel 4 to 5 ... channel number capital N. How I will be hopping will be depending upon a PN sequence code. This sequence will be inherent to a system designer and the type of the design that you are doing. So, the key of this whole system design is the design of this secret PN sequence code. The data modulation that will be going in between will be of different types. It can be a coherent type of modulation or it can be a non-coherent type of the modulation. The famous non-coherent type of the modulation that is usually used for these frequency hopping space spectrum systems are the MFSK, the multiple frequency shift keying, or the differential phase shift keying. For MFSK, we within a single hop time 2 or more frequency offsets are possible, whereas for our differential phase shift keying, a fixed number of the symbols are placed per each hop. A good example of this DPSK is the Milstar MDR or the Milstar medium data rate systems. Now, coming to the coherent modulation type of frequency hopping system, this kind of the system utilizes sync word, which is utilized for getting the synchronization information. By means of synchronization, I mean the phase and the timing estimate that will be performed at the front end of the receiver before any kind of the dehopping and the data detection techniques. The scheme requires basically of two phases. In the first phase of the coherent modulation frequency hopping system, you will have the phase, timing and the frequency information extracted by some estimation technique, and in the second phase only you can demodulate the data. A very good example of such system is the crosslink of GPS or the global positioning system. Frequency hopping space spectrum system further can be classified into two types. One is the single channel frequency hopping and the second one is the multiple channel frequency hopping. See, for the single channel frequency hopping, only one hopping carrier will be there operating over whole bandwidth, and in multiple carrier frequency offset, obviously we will have the multiple carrier frequencies. Each of these carrier frequency is getting hopped simultaneously over the whole bandwidth available based on the PN sequence code you have generated for the typical system. Before entering into the system design, typical transmitter receiver design and seeing the block diagram of transceiver for FHSS, let us understand some of the terms of it. Number one is the hopping range. It is a very important term. Usually, the hopping frequency range signifies the difference of the lowest and the highest frequencies, carrier frequencies getting utilized in the system. The hopping bandwidth correspondingly signifies the channel bandwidth that is needed to pass this whole range of the hopping frequencies. Usually, the hopping bandwidth will be denoted by W, and the bandwidth of the data modulation will be given by B into WB. See, given a typical hop, that bandwidth will be denoted, modulation bandwidth will be denoted. The receiver, after synchronizing, it will de-hop the received signal, and hence after this de-hopping, the signal that will be ending up with is called de-hopped signal. Similar to the direct sequence spread spectrum system, here also we will be interested to know what will be the definition of the processing gain. Remember, the fundamentals of the spread spectrum communication system is that whenever you are spreading over a given bandwidth, then you will be always ending up with a kind of the processing gain associated with it. The processing gain here will be defined by the W divided by the bandwidth of the modulation, where W is the first null to null bandwidth of your available channel, and BWB is the data bandwidth, that is also taken as a twice of the bit rate. Here we enter with the single channel transmitter design of an FHSS system. As told, here will be a single carrier which will be hopping over the available bandwidth. Here the carrier is given by cos omega naught t, and the incoming data stream, the dt, he is modulating the carrier frequency cos omega naught t. After data modulation is performed, here is a code generation circuit where you are generating the PN code that will help to hop this carrier over a wide range of the bandwidth available. The signal obtained here at this point is already the spread signal, frequency hopped spread signal, which is further passed to a band pass filter to give a shape, a proper shape, and to finally form the frequency hopped signal that will be transmitted via the antenna. Remember, in the whole system design, this code will be performing the key part of the design, which will be uniquely known to a specific kind of the transmitter and the intended receiver. Frequency hopped spread spectrum receiver will be just on the other side, where it will work like this. The hopped signal you have received from the antenna front end, which will be required to be passed via the wideband band pass filter. He will capture the whole range of the hopped signal, which is equal to capital W that I have showed earlier. And if you are following a coherent system, then you need to extract the synchronization information from the received signal, which is done in this block. The synchronized signal is fed to the PN code generator and also is required to the data demodulation to keep a sync between the code generation and the data modulation. The frequency synthesizer synthesizes the hopped center frequencies according to the PN code generator instruction, and this is a multiplexing unit who is helping us to de-hop the signal with the locally generated PN sequence code. So, once you are here ending here, you are getting the de-hopped signal. Remember, this de-hop signal again we need to pass through a band pass filter, because he will eliminate the some frequency term from the de-hopping operation. After this band pass filtering, you are ready for the demodulation, and this synchronization information will help you to be in the sync of the code generation and the demodulation. Detected beats are obtained here. So, this is the overall structure, the way the frequency hopping spread spectrum system works for in the transmitter as well as in the receiver. Now, coming to the types of the frequency hopping space spectrum system. So, there are basically two types based on the rate at which you are hopping. We call it a fast frequency hopping system or a slow frequency hopping system. The slow frequency hopping system I would like to mention first, where the slow frequency hopping system you will be getting 2 or more number of the symbols per frequency hop time. So, I should tell here what is the hop time is. Suppose we started with this diagram. So, we have a wide bandwidth W which we divided by number of the channels, and my center carrier frequency is hopping over this different channel based on certain pattern. What will be the hopping pattern? That will be governed by my PN sequence. Fine. But what is the hop time is the duration between which the carrier frequency will be hopping from one channel to the next channel. So, it is basically the time that it is spending within a channel before hopping to the next. So, what is this slow frequency hopping is, if I think that for 2 or more number of the symbols that I am transmitting from transmitter to receiver, this hopping frequency is not changing, then we call it is a slow frequency hopping. On the contrary, for the fast frequency hopping, within a symbol transmission, the carrier frequency may hop from one channel to the next. Another one is non-coherent or differentially coherent modulation techniques. It has a maximum popularity for the frequency hopping space spectrum communication system design because of the so many reasons. As we understand that for coherent modulation scheme, we need to have a sync word associated with it, which will help us to extract the phase, time and frequency information in the receiver. So, it is an extra burden to us in the receiver, and sometimes it becomes an extra hurdle for us to extract the information correctly, so that the dehopping operation can be done perfectly in the receiver. To avoid all that, people have preferred the non-coherent kind of the modulation scheme for this frequency hopping space spectrum system design. It is very hard. The main difficulty comes from the maintenance of this phase coherence in the frequency synthesis and over the different hopping bands involved. However, there are several new systems coming up where this coherent modulation is considered over the frequency hopped signal. In a frequency hopping space spectrum system, in context of the jammers, there is a very important concept of the rate of the hopping. How is it coming into picture is something like this. Suppose let us consider this situation where we have a transmitter transmitting, and here is my intended receiver who will be receiving. And however, this is the location where my jammer is sitting, and he, as it is a wireless communication, so jammer is in the range of this transmitter, and he can hear whatever is getting transmitted on air. The jamming device, it can intercept the hopping signal, it amplifies the received signal, and he again retransmit it, so that actually it reaches to the receiver. Think of a situation, if the jamming signal can reach in the receiver exactly within the duration where actually the transmitter's signal is getting received through the path of x1, then you are in trouble, because the jamming power is much higher than the power that is transmitted from the transmitter and basically getting received by the receiver through this direct path. So, your intended signal will be completely buried by the jamming signal, and you cannot be able to retrieve your own signal in the detection process. Now, with respect to a jammer, to be a successful jammer, what you need to do is for an efficient jamming, you have to reach in the receiver within the same hop where actually the transmitter signal is transmitting. For such kind of the jammers, we call it is a frequency follower jammer, and the underlying assumption is that the jammer could crack the PN sequence code that you are using to hop in the transmitter. So, he can also hop in the same pattern like you. So, you are in trouble, and additionally if he can reach you within the same hop, your detection process will be in high trouble, because his transmitted power, jamming power, will be higher than your transmitting power. Now, let us see a little bit what will be the typical boundary zone within which actually the jamming signal will be really very effective with respect to the receiver detection. So, from the figure we understand that the signal that is traversing from the jammer is following the path x2 plus x3, and there is another time involved inside the jammer, which is called the processing time, which is basically taken for the amplifying of the signal. So, to become an effective and following jammer, frequency follower jammer, what is required is, see, you need to traverse like this. I mean, your jamming path is going via x2, your jamming path is going via x2 to x3, and this is your intended transmitting to receiving path. So, the equation should be something like this: your x2 plus x3 divided by 6, this is a time taken by the signal to traverse via the jammer. This is the extra processing time that the signal is getting processed, getting amplified inside the jammer, and x1 by c is the direct path between the transmitter to receiver. The signal is taking this much time to receive from transmitter to receiver. And what is this extra term we are introducing is, this is a hopping time that carrier is hopping between the channel to channel in the receiver, and alpha is the extra fraction of the time that actually when the hop is in the hop, there is no hit. Hit means within that you could not reach. So, basically 1 minus alpha into the processing time, that into that time, that will be the hit. Sorry, it will be a TH. So, it will be, there will be a hit. So, once actually you are hitting the time, so the total time that you are elapsing in the jamming path, that should be, if it is less than equal to this alpha TH plus x1 by c, then this is a effective jamming. You should be able to succeed in jamming the whole stuff. If we rearrange the last equation, we will be ending up with this x2 plus x3 should be less than equal to x1 plus c into alpha TH minus t proceeding, as is shown in the equation number 3. And if we are in the right hand side, if we change this inequality equal to the in an equal sign on the side, basically what we are ending up with is this region of the permissible operation of the jamming is basically being inside an ellipse, what is shown in this figure, where transmitter is one focus of the ellipse and receiver will be the another focus of the ellipse. And if we turn the ellipse with respect to the x1 axis, it will form an ellipsoid, and that ellipsoid will basically give you the boundary of the jamming zone. So, in order to be a successful jammer, you have to be within this jamming boundary. Obviously, so if I am reducing the TH, I mean the time of hopping, that means your rate of hopping is increasing, then obviously the total area under the ellipsoid, that will be decreasing. So, that is your target area as a system engineer. You try to decrease the boundary zone and the total area under the ellipsoid, so that actually your receiver can be resistant against the jammers. A few more consideration, and now we will enter slowly inside understanding of MFSK data with an MFSK data modulation, how the frequency hopping spread spectrum system would look like. Let us consider that capital Fi is the modulation frequency, and this modulation frequency is in the ith modulation, at the ith modulation tone. Remember, we are choosing the ith modulation tone from a set which is having capital M number of the modulation frequencies. So, it is something like that. I have a set of the modulation frequencies, as it is a frequency shift keying. So, I may have suppose 4 different a set which is having a 4 different frequencies to select for the modulation of the for the data modulation basically, and there is another set which we are calling as MH, which is actually talking about the how many number of the hopping frequency set you are having. So, for a ith time, at ith time I will have a choice of any one data modulation frequency which I will call as capital Fi, and for this capital Fi I will choose another set of the hopping frequency from this set which I will call as small fi. Okay. Remember that for a typical modulation, data modulation, I may select multiple if it is a fast frequency hopping, multiple hopping frequency, and otherwise if for a multiple number of the modulation data modulation, I can actually choose a single hopping frequency which will be a slow frequency hopping system designed in that case. And this capital MH is having a quick relation with the number of the bits that you are taking for the frequency synthesizer design. We is generating the code for this hopping, and this capital MH is hence can be written as 2 to the power k. So, for example, if I have a 3-bit frequency synthesizer, so I can generate 8 different set of the frequencies for hopping. Correspondingly, I have 8 channels over which my carrier can hop. Remember, if I am having a total bandwidth of W which I started, so now this whole W will be basically my MH into del f. MH is what? MH is the number of the center frequencies which are available for my hopping, and del f is the difference between that center frequency. So, it is basically this guy del f which is telling the difference between one center frequency to the next. So, the total bandwidth, hence this W can be now written in the terms of number of the hopping frequency available and the frequency gap you are having between two corresponding hopping frequencies. Theta I is a random phase variable that is that will invariably will be added and it is statistically independent for both this small fi and the capital Fi. This random phase will be automatically associated with the generation of the hopping signal and the frequency modulation process. So, we will be next slide we will be handling with capital Fi, small fi, capital M, small capital M, capital MH, the bandwidth W, and this independent phase component theta I to show you the modulated and transmitted frequency hopped signal. Thus, we are considering a slow frequency hopping signal. So, let us start with it. We chose the data modulation frequency Fj. So, I wrote that j can vary any value and j can and I have a capital set M from which I am choosing this Fj. So, if j is equal to 4, so I will have F1, F2, F3 and F4, capital F1 to capital F1 to capital F4 to choose. Theta j is the random phase associated with it. Like a direct sequence spread spectrum system, here also we are having a pulse, rectangular pulse who will be transmitted and which is having a unit height. The duration of that pulse is equal to capital T second, and the pulse is starting at the time will be T0 and hence A will be the A square is the power of the transmitted signal. PTH is the pulse, rectangular pulse associated with your hopping pattern, and TH is equal to your hopping time. Small fk you have chosen from your MH or MK here, and you are having a several set of the hopping frequencies that you are choosing, and small k here is denoting here how many number of the such frequencies you are having in your data bank. So, this is the total transmitted signal, frequency hop transmitted signal. Basically, you will see this is the product of the complex envelope of the data modulation getting multiplied with the complex envelope of the frequency hopping. The RF signal of it will be simply the real part of this whole section, and if we are expanding this exponential term here, we will be ending up with this only the cos term in the equation shown in the equation 6, and this will be the simplified for next is the simplified form of the transmitted signal. So, TH was our hop duration, TS is the frequency modulation time duration to us, and if this is the channel bit time duration. So, we have already seen in the last slide that the transmitted real the simplified form of the transmitted data symbol will be a combination of this TH and the TS. Remember, there is a nice relation between this TH and TS. If it is a slow frequency hopping, we will get a integer number if I divide the TH with the TS, and is basically telling the how many number of the MFSK symbols are getting you are transmitting per hop. Input data stream here will be composed of the channel bits, and the channel bits will be given the relation between the channel bit duration and the symbol duration is as usual will be given by this TS equal to TCB log m to the base 2. With all that understanding, and if the channel bits are not coded, we can understand that the bit time will be simply equal to the channel bit spacing, as the coding is not involved, and hence we can write this equation. Now, fundamentally we are ending up with the understanding that if we are given the TH number, TH seconds for hopping, and we have the n number of the MFSK tone symbols to be transmitted, each of the symbol is having a duration of this TS. So, definitely n into TS will construct the hopping duration TH. And the difference, the frequency separation del f that we have discussed earlier between two adjacent hopping frequency can be a very few hertz, and it can be a very large for far apart signals, far apart center field frequencies, it will be even several kilohertz also. At the receiver, this dehopping synthesizers will be used to dehop the signal, as I have shown earlier in the receiver design, and using that whole concept, and we will be now seeing a very nice hopping modulation process with a nice example in the next session.